Hi, I'm Sandeep Neema. I'm a program manager at DARPA Information Innovation Office, and I'm very excited to present to you the DARPA Assured Autonomy program. We'll be talking about the core technical challenges that this program is interested in addressing and provide some of the parameters of the program in the description. Autonomous systems and autonomy are critical to many current and emerging DoD mission needs. Several reports and studies underscores the importance of autonomy to DoD. The U.S. Army Robotics and Autonomous Systems Strategy Group identifies several new mission capabilities that will be enabled by the use of autonomous systems. I'd like to submit that the challenge that we face is not so much in building of these autonomous systems, but providing an assurance that these systems will be safe and perform as intended. The DSB report on autonomy that was released in summer of 2016 comes up with the same conclusion and recognizes that the decision for DoD to deploy autonomous systems should be based on trust that they will perform effectively and that such use will not result in high regret unintended consequences. An example of a high regret unintended consequence is the much publicized Tesla crash, in which the vision system on the car was unable to sufficiently distinguish a white truck against a blue background as an obstacle to be avoided, and it resulted in a fatality. So it's clear that in the absence of trust, these autonomous systems will not be adopted and deployed. That said, however, the problem of delivering trust for autonomous systems remains insurmountably hard. The RAND Corporation's report on driving to safety concludes through statistical analysis that to demonstrate with sufficiently high confidence that the systems will be as safe or better than human operators would require exorbitant amounts of testing and time in the order of billions of miles and hundreds of years to come up with the same level of assurance. The OSD Test and Evaluation VNV Strategy Report comes up with a similar conclusion and states that the standard practice of testing all possible states and all ranges of inputs to the system is an unattainable goal, and that a fundamental change is needed in how we validate and verify these systems. So these studies and the state of art motivates the goals of this program. I'd like to draw your attention to three key elements from the goal statement. Learning-enabled autonomous systems. We contend that learning is going to be paramount to achieve any higher levels of autonomy in the system. Since these systems will learn and evolve, any notion of pre-deployment assurance that's valid for entire lifetime of system is not tenable, and we would need techniques to provide continual monitoring and assessment of assurance of the system. These systems will operate in adversarial environments, which are highly dynamic, evolving, and include several passive and active objects, some with hostile intent. And it's important to guarantee safety and correct operation of these systems in such environments. So the goal of the program is to build design and analysis tools that can provide continual assurance of learning-enabled autonomous systems to guarantee their safety properties. To frame the problem, let me provide a quick pedantic example of what a learning-enabled system is. Brake-by-wire system that you see in most cars today. Such a system takes inputs from the driver through the brake pedal and delivers braking force to the wheels. For such a system, a safety requirement may be that when the driver applies the brake, the vehicle should come to a complete halt, say within 5 seconds. Now, for such a system and such a safety requirement, with current technologies, we're able to provide a safety assurance that the system will indeed do so. Contrast that with an automated collision avoidance system, which uses the brake-by-wire system, but now inputs for the braking could come from learning algorithms. Say, for example, a perception algorithm, a trained neural network that's been trained to recognize pedestrians and other obstacles in the road ahead. The system may incorporate other forms of learning. Say it learns the dynamics of the braking system, particularly as the braking parameters change and the system degrades, or as the road conditions change. Now, for such a system, the safety requirements may be a little bit more expansive and may state that the vehicle should come to a complete stop when it detects a pedestrian in the road ahead. Now, for such a system and such a requirement, we currently don't have technologies to provide a safety assurance. Since we're talking about safety assurance, let's look at what the state of practice is in providing safety assurance for systems today. The systems engineering process that we follow in most systems today consists of three focus areas: conceptualization, that is stating what we want; engineering and build, that is how we get what we want; and certs and assurance, that's validating that what we got is what we wanted. So an assurance case is a logical chain of reasoning to establish claims about a system with provided evidence. The claims are typically safety and security related. In our example that we looked earlier, the top level claim might be that the vehicle should come to stop, And a secondary claim from that may be that the sensor that detects the driver input correctly recognizes the driver input. Now, in the current practice, the evidence for such claims is extracted primarily from system testing, and as a result, the assurance case is limited by the amount of testing coverage we can get. The state of art uses model-driven design and adds rigor to the overall safety assurance process. In model-driven design, the design is primarily conducted with formal models of the system. These models may include structural models, including architecture and interconnects of the components and systems, may include behavioral models such as finite state machines and ordinary differential equations. The use of these models enables mathematically rigorous techniques such as formal verification that can provide comprehensive guarantees about correctness of properties of the system. Use of model-based methods also enables simulation-based approaches. Models still, however, are an abstraction of the physical reality and make simplifying assumptions. So it is imperative that we still use system testing to validate the models. So overall, as a result of combining these methods, we get a much stronger and rigorous assurance case, the validity of which is only limited by the accuracy of the models and the test coverage. This approach gains increasing ground in industry. However, it's only applicable to non-learning systems that operate in well-characterized environments. Now, what happens when we add learning to the system? Well, clearly we can add learning components, as we saw in the example earlier. However, these type of components are using data-driven learning, which means that their operational behavior is a function of the data that they train upon, and as a result is very difficult to characterize and predict. Data-driven learning introduces uncertainties in the overall design process and may result in unpredictable emergent behavior in operation. Now, what happens to our assurance approach? Well, we currently don't have techniques with which we can model these learning-enabled components. As a result, we cannot use formal verification methods. We don't have techniques for doing formal verification method. The consequence of that is that we don't have an approach to build an assurance case for these learning-enabled autonomous systems. The lack of predictability that results with using learning-enabled components requires that we rethink an approach to assurance. So what is the key idea that we want to pursue in this program? Well, let's look at it with this conceptualization. The figure on the top right is a conceptual representation of the state space of a system. When speaking of safety properties, it's common to think of it in terms of reachable portions of the state space and unsafe regions of the state space. The goal of safety verification is to prove that the reachable portions of the state space do not overlap with the unsafe regions of the state space. Let's concretize this further and pretend that this is a two-dimensional system, in that we have a way to measure the distance from where the system currently is to the unsafe region of the state space. Now, given that distance measure, we can clearly build a controller that will continually steer the system away from the unsafe region. And we can formally verify such a controller and provide an evidence that that is indeed the case. Now, what happens when we look at systems that include learning-enabled component? Well, let's take this example further, and instead of a distance sensor, let's replace that with a perception-based estimator that gives us a distance estimate based on some other features in the region. So a couple of things to note from here. Well, the distance estimate that you get from such a perception-based system are bound to have inaccuracies in them. More importantly, the quality of the estimates will depend on what the data it's seeing at operation time versus what the data was trained with. So any statement that you can make about the correctness of this estimator are bound to be conditional based on the data it trained with. So that's what we mean by conditional estimate. So now in such an environment and learning-enabled system, any notion of assurance is bound to be dynamic because the data that the system operates upon are not knowable a priori at design time. So at best, we can provide conditional estimates of assurance and update those estimates at operation time. So that's what we mean by assurance measure that's being estimated dynamically. When you look at this figure and you're operating in different regions of the state space, when you're far away from the unsafe region, it's sufficient to know the level of assurance and continue operating in the system. But when you're close to that unsafe region, it's not sufficient to just know the assurance measure, but you need to take active measures to avoid the system from entering into the unsafe region. So for that, we want to include hard constraints and monitor and guard against that to prevent the system from entering those unsafe regions. So that's what we mean by monitors and guards here. Outside of the known unsafe region, the system is free to operate and explore, and that overall approach we refer to as safety-aware learning. Now, to enable this, we will need innovations in system modeling. We'll need new formal verification that can provide these kind of conditional estimates, and we'll need new simulation-based methods. So the development in program spans three technical areas. TA1 is design for assurance, TA2 is assurance monitoring and control, and TA3 is dynamic assurance. The design for assurance includes design technologies that will deliver evidences of safety and correctness for these systems. We contended earlier that the evidence that we get, we may not be able to get comprehensive evidence all during design time, and we would need to provide conditional evidence, which will need to be updated during operation time. So the conditions that need to be monitored will need to be provided by the technologies in the TA1 area. Some of the technologies that we anticipate needing for the design for assurance include innovations in modeling technologies, formal verification, simulation-based testing, and system testing. The TA3, or the dynamic assurance, is partitioned into design portions as well as operation time. At design time, we build an assurance case that includes conditional evidences as well as unconditional evidences. And these conditional evidences are then turned into a dynamic assurance case that's monitored and evolved at operation time. The conditions for these conditional evidence will need to be analyzed and monitored by the technologies in the TA2 and provide updated estimates, which can be used to evolve the evidences in the assurance case. Now, what can you do with an assurance measure? Well, one common problem in mixed initiative control is that the operator loses situational awareness, and when you perform a handoff at an arbitrary time point, then the system may get into worse state. And to avoid that situation, a continuous measure of assurance may help bring the operator gradually into awareness. But more directly, an assurance measure could also be used in a control loop where you use the assurance measure to guide the learning algorithm. So that's what we mean by safety-aware learning here. So looking further at the TA1, the goal of TA1 is to develop and integrate tools for design and verification of learning-enabled systems that can generate evidence of safety and correctness. Some of the core research challenges in TA1, we are looking for technologies that can provide compositional architectures for learning-enabled systems that intrinsically guarantee and preserve some properties. This may include things like passivity-based architectures or time-triggered architectures that intrinsically guarantee stability properties of the control algorithms. We're interested in formalisms, abstractions, and domain-specific modeling languages for representing learning-enabled components, systems, and their dynamics. We're interested in scalable methods that address formal verification of safety and liveness properties of learning-enabled cyber-physical systems. Specifically for formal verification, our interest is in techniques that can provide formal verification of machine learning algorithms. We're also interested in simulation approaches that can drive the learning-enabled system to elicit unanticipated behaviors. Some of the conditions that will need to be monitored by operational techniques, we will need transformation tools to automatically synthesis assurance monitors that can be monitored by the operational technologies. The goals of our TA2 is to develop algorithms for safety-aware learning and techniques for monitoring and enforcement of safety constraints. In this TA, the core research challenges include techniques and algorithms for safety-aware learning, and you see a representation of that in the figure there. In this work that's been referenced here, researchers have developed methods for integrating safety constraints into reinforcement learning. In the example that's demonstrated here, the platform is learning its own dynamics while completing a mission that involves navigating from the floor to the ceiling. And a sudden change in the environment is introduced by introduction of a wind gust. And in their case, the platform is able to learn the new environment and is able to adjust its control regime to operate safely in presence of that changed environment. Other challenges that we're interested in for enforcement of hard safety constraints. And here we're looking both for instantaneous verification of instantaneous constraints, but more importantly, techniques to provide prediction and being able to sort of look ahead for future violation of constraints. So these may include techniques like online verification, symbolic verification, reach avoid kinds of techniques. We're also interested in techniques that can detect data distribution shifts and quantify the performance of learning. Typically, machine learning algorithms, classifiers, their performance depends on the data that they trained with versus the data that they're operating on. And if the data that they're operating on belongs to the same distribution as what they trained on, then their performance is good. Whereas if they diverge from the data set that they're trained on, the performance degrades. And so the important challenge here is to build tools that can detect data distribution shifts and qualify the performance of the learning algorithm. The goal of TA3 is to develop tools and algorithms for formal representation and evaluation of assurance case. Assurance cases have typically been used for certification as an artifact that's audited by human inspectors. In the program, we would like to extend that by providing formal semantics and building tools that would enable these assurance cases to be machine processable and evaluatable. We're looking for scalable algorithms that can provide dynamic evaluation of assurance cases consistent with the formal semantics. Since these assurances can be significantly large, we're looking for capabilities to modularize assurance cases and automatically generating assurance cases based on system description. And in the program, we're also interested in application of these tools to produce dynamic assurance cases for learning-enabled cyber-physical systems. The TA4 is the integration and experimentation platform. These will be the candidate autonomy platforms that can serve as test beds for experimentation, evaluation, and demonstration. Some of the key characteristics of the platform that we seek: the platforms have to be DoD relevant in order to demonstrate the assured autonomy technologies. The platforms have to be autonomy capable already or readily extensible to include autonomy components. And most importantly, these platforms have to be accessible to performance either directly or through high-fidelity simulators or surrogate platforms that the other technology developers in the program could use. Just to provide an illustration, here is an example of a notional platform. Consider an autonomous surface ship. For such a platform, we would want the TA4 performers to define an experimentation vignette that can be used to test the technologies and provide assurance for during the course of the program. So in this context with the surface ship, a vignette may be collision-free navigation in open seas. It may also mean autonomous trailing of other ships. Some of the kinds of learning algorithms that could be integrated or already integrated, and they're progressing. The complexity of the learning algorithms is progressing across phases. So first phase, we anticipate that classifiers, which are commonly used, could be integrated into the system. In case of the surface ship, that may provide assistance in visually recognizing objects and inferring the capabilities of the ship and influencing the collision regulation behavior. In phase 2, that may progress towards much more advanced learning algorithms, reinforcement or imitation learning, which may learn, if it's doing a trailing mission, may learn evader tactics and determine the course of action. And in phase 3, we may look at techniques for learning the system dynamics, being able to predict the dynamics of the evader ship and even learn dynamics of the own ship. The assurance that will need to be provided by a combination of the TA1, 2, 3 technology developers would mean to develop an assurance case for the collision regulation in phase 1. In phase 2, that would be developing assurance case for collision regulation under the reinforced learning guided behavior. In phase 3, that may mean developing assurance for trailing under the RL guided behavior. The demonstration could progress in phase 1. It could be a simulation-based or software-in-the-loop kind of demonstration. But in phase 3, we would like to see physical demonstration either on the platform itself or a surrogate of the platform. These are the anticipated interactions between the TA performers. The TA4, as we noted earlier, is the primary challenge problem developer and will share platform definitions and challenge problem scenarios with the TA1, 2, and 3 performers respectively. The TA1 performers are expected to learn about the platforms, understand the challenge problems, and apply their tools to build evidence and conditional evidence that could be used by the TA3 to put together a comprehensive assurance case. This assurance case would be dynamic, and the conditions for this assurance case would be monitored by the technologies developed by the TA2 performers and would provide monitored evidence that could be used to update the assurance case during operation time. The TA2 may also deliver novel learning algorithms or safety integrated learning algorithms in the form of operation time components that will need to be integrated by the TA4 performer within the platform. Some of the key objectives for the programs. One major challenge that the assurance technologies face relates to the scalability of the algorithms. In cyber-physical systems, the curse of dimensionality is a well-known problem. And our goal in the program is to increase scalability of the design time assurance techniques. In your proposal, describe the baseline capability of the proposed method in terms of the hybrid state space and number and complexity of learning-enabled components in the system. You should also describe how you plan to scale up your assurance approach by an order of magnitude during the course of the program. In case of performers who are using multi-fidelity methods, modeling abstractions, you should characterize the trade-offs between the fidelity of the modeling abstraction and the scalability of the verification approach. Since we are considering doing online V&V of the system, we are concerned with the overhead of operation time assurance. And so a major goal of the program is to reduce overhead of operation time assurance. In the proposals, you should describe the baseline overhead of the operation time assurance monitoring techniques and describe how your approach will minimize it to be no more than 10% of the nominal system resource utilization. The dynamic assurance case, we expect that to be a sizable artifact. And again, the proposal should describe the size and scale of dynamic assurance case that can be developed and evaluated with your tools. One major challenge, as we noted earlier, with respect to V&V of autonomous system is the sheer number of trials required to deliver assurance. And the expectation is that the use of these modeling and verification method would help to reduce the number of trials to assurance. In the proposal, you should describe how your approach can quantifiably reduce the need for statistical testing. These are some quantitative program objectives, primarily for illustration purposes. We expect that you should develop and describe your own quantitative metrics specific to the approach that align with the objectives that we describe here. It's typical for cyber-physical systems to express their complexity in terms of number of continuous state variables. A simple quadcopter with a 6 degree of 6 model easily entails 10 plus dimensions. And for a large complex system with other objects in the environment, the complexity may be order of 100 dimensions. The current practices don't support V&V of learning-enabled component, but we would like to expand that across phases to increase the number of learning-enabled component system as well as their complexity. The dynamic assurance case, we anticipate that initially it may be low complexity in the order of tens of conditional evidence and grows towards thousands of conditional evidence in phase 3. Similarly, for reduced trials to assurance, we start with 10 to 100,000 physical trials, and during the course of the program, we'd like to reduce it by an order of 3 orders of magnitude. This is the schedule of the program. It's 3 phases. The first phase is longer, 18 months, to support the initial development of the technology and prototyping the tools, as well as establishing interaction with other performers. The TA1s, TA1, TA2, TA3 plan on providing experimentation support in the last 6 months of the phase. For the TA4 performer, we expect the initial challenge problem development to take 6 months, and then the rest of the period is used to perform integration execution with the rest of the performers. The schedule is for guidance. You should provide your own schedule specific to the technology that aligns with the schedule. We plan a kickoff at the beginning of the program, 2 PI meetings in the first phase, followed by a demonstration at the end of each phase. The second and third phase both have 1 PI meeting each at the middle of the phase. In the third phase, we plan a capstone demonstration of the technologies. The summary of the overall programmatics, as I mentioned earlier, it's a 3-phase program, 4 technical areas. We anticipate multiple awards in TAs 1 through 4. We anticipate 2 TA4 platforms to demonstrate that the tools that we're developing are agnostic to domain and platform. The TA4 performers would also be providing the demonstration as well as evaluation of the TA1 through 3 technologies. As such, proposers selected for TA4 will not be selected for award as a performer on TA1 through 3. In the TA4 proposal, you should plan to support at least 2 TA1 through 3 teams in the base effort and include options for supporting additional TA1 through 3 teams. We expect the TA1 through 3 proposals to apply the technology to both TA4 platforms, but in terms of proposing, you should include one platform as a base effort and support for the second platform as an option. We encourage, but we don't require integrated TA1 through 3 proposals. Proposers who are submitting to TA1 or 2 only should anticipate that they would be joining an integrated TA1 through 3 team after the program kickoff, and should include in their description interfaces and plans for working with other TAs. As you noted in the interaction, it is important that all the TAs and all the performers are working together to achieve program success, and we would be including associate contractor agreement in the awards. Some more description of the programmatics of the TA1. In your TA1 proposal, you should describe at least one example of a problem. Think of that as a surrogate for the challenge problems that will eventually be proposed by the TA4, and demonstrate for the challenge problem how your technique can be applied. Clearly describe the metrics and the milestones that will be reached at the end of each phase. The TA1 efforts are expected to deliver tools that will need to be integrated into design flows for learning-enabled cyber-physical systems. The proposal should clearly explain the interfaces for integration. TA1 performers will need to work closely with the TA4 to learn about the platform and apply the techniques to the provided challenge problems and consult with them on application techniques to target platform. TA1 platforms should demonstrate their tools on challenge problems and provide evidence that TA3 can use to build a dynamic assurance case. In the TA2, similar to TA1, provide description of a challenge problem where your technique is applicable and describe the metrics and milestones that you can reach at the end of each phase. The TA2 effort should deliver operation time components that will need to be integrated into the TA4 platforms. And as such, the proposal should clearly describe the interfaces for integration. Similar to TA1, the TA2 performers are expected to work closely with TA4 to learn about the platform and apply their techniques to the platform and challenge problems. The TA2 also need to work closely with TA1 because the conditions that their methods will need to monitor and any assumptions that they have will be provided by the TA1 performers. The TA3 proposers, similar to 1 and 2, should also describe a challenge problem on which they can apply their methods. Now, the TA3 effort is going to result in a dynamic assurance case for the specific challenge problem using the tools to build and evaluate the assurance case that will need to be integrated into the TA4 platform. The TA3 performers need to work closely both with TA4 and TA1 and 2. They should work closely with the TA4 performers to learn about the platform and formulate a dynamic assurance case and work with the TA1 and TA2 performers to guide the development of specific evidences that they will need to provide. The TA3 performers will lead the effort to integrate the evidence developed by researchers into a coherent assurance case. The TA3 performers will also need to work with TA4 performers to deploy the assurance case in the platform. The TA4, as a platform developer, has a significant role in the program. They will be responsible for demonstrating the tools applied to the platform-specific challenge problems at each demonstration meeting. They should evolve their experimentation platform, if not already equipped with learning technologies, to extend with learning component. They will need to develop challenge problems as well as define evaluation scenarios. They need to provide a framework and access to the platform for the technology developers so that they can integrate the learning-enabled components. They should provide models and access to any other development tool chains that they're using and validate the assurance that's developed by TA1 through 3 performers. It's important that the platforms that they identify, sensors, computing hardware, any software, should be unclassified for the performers to be able to access and work with it. For working together with other performers, they will need to educate TA1 through 3 performers on their use cases, as well as technical challenges in building assured versions of the platform. They need to develop unrestricted and unclassified challenge problems that can abstract the key difficulties for use by the performers. And they'll need to apply the research results from the other TAs to the development of the Assured platform. Thank you for listening to the presentation. We look forward to great ideas and proposals on this important topic.